Hi, welcome to Precalculus. Today's topic is matching polar equations with their graphs. So as you see, typically three equations are given, and then underneath it, six pictures are given, and you're supposed to match the equations to the pictures. So let's go review what we have learned in the last few lectures since we started the polar coordinates. And the matching can be done very quickly if that's what you want to do. And of course, if you want to do a full-scale job, then you have to do point plotting. The objective here is to recognize pictures quickly and move on. It's not point plotting style. So let's see what have we done. We have talked about Lemniscate, characterized by having a square or square root somewhere. And with cosine it was horizontal, with sine it was 45 degrees. So that quickly tells us that the very first equation that we have here, the clue is being this square, that it's a lemniscate. You remember that means a ribbon. So this is our nicest ribbon. With sine it was going to go at 45 degrees, which this one does, and that number is square of the radius, so the radius will be 2. So it's obvious that this one then will be choice A. What else had we done? Okay, here for the lemniscates we had the case of roses. So the roses was characterized by just a number times sine or cosine of a multiple of theta. The multiple, if it was odd, like 357, we had this type of pictures. If it was even, the number of petals uh, doubled. So here is a petal with a rose with n being 3 has 3 petals, n equal to 5 is 5 petals. Here n equal to 2 has 4 petals, and n equal to 4 has 8 petals, and so on. We noticed previously that the case of sine and odd n splits into two cases. For 5, 9, 13, increments in steps of 4. Fixed point is up here. And for 3, 7, 11, these also go in steps of 4. Fixed points at the bottom. So do we have a rose here? Let's see, do we have a rose? Well, here we have sine of 2 theta, and that is an even number, so it's going to have twice as many petals as the number you see as a multiple of theta. So that has to be case E. That is. Now, what else had we studied? Well, after the roses, we had limacons and cardioids, etc. So it was a number plus another number times sine or cosine, and depending on if you're adding or subtracting. So adding a cosine, you kind of build your picture toward the right. Subtracting a cosine, you build your picture toward the left. And with a sine, it goes either up or down. So if you're adding a multiple of a sine, the picture builds upward, and if you're subtracting, it builds downward. So of these cases, they had names for themselves. So this was with a loop. This is called the cardioid, which looks like a heart. This one is called the dimpled limason, and that one was a convex limason, depending on the relationship between A and B. So what do we have here? Do we have a limason? Well, item number 3 here is 2 minus 3 cosine theta. Now you can do picture matching, or you can do testing of single points to see what we get. So first of all, what are the limaçons in this picture? We have this one and this one. So the competition is between these two. Which one of them would it be? We had mentioned that with the cosine, we building horizontally, either left or right. With minus, we were going left, and plus, we were going to right. If it were sine, with minus was building downward, and plus it was building upward. So all indications is that this has the matching f. Now we go ahead and double check certain points to make sure we are on the right track. For example, when theta reaches pi, its cosine will be -1, and r has to be 5. Does this look like it's hitting 5? We are at pi, we are hitting 5, and that rules out case C. It has to be case F. So we have two reasons to believe it's case F. Or you can go and match against the picture we had up here, down here, and where was this? So it says if A is less than B, we had 2 minus 3. So yes, in our numbers 2 is of course less than 3, so we get a looped limits on building toward the left, and that is the final answer there. So we had of course circles. Also we don't have a circle up there, so with the cosine, again you're building horizontally, plus cosine on the right, minus cosine on the left. With sine you build vertically, plus sine on the top and minus sine on the bottom. Finally we had the case of lines, and well, lines and circles I should have written. With r equal to a number, we have well, that's the simplest picture. It's just a plain circle. Theta equal to a number, that's going to be a ray at that angle. Our cosine equal to a number is going to be a vertical line. So A is positive on the right, others on the left. Our sine equal to a number is going to be a horizontal line, and again positive A on the top, minus A on the bottom. So these are the pictures we have studied. Now of course you can go challenge yourself to more complicated pictures, mix and match the kind of things that you had here. I might as well go and see if I can find something for you guys. Let's see, do I have something here? Yes. So this is a region of the characterized by the following polar inequality: r less than sine of is a over b some number, a and b decided here, and you can create a variety of pictures. So for example, this is one possibility, here are other possibilities, and so on. A lot more complicated than what we have looked at so far. Okay, so lecture today is short. You're just matching. You want to go through quite a few of these exercises to have them imprinted on your mind. Applications are going to come up in calculus. There, these curves are also still a mathematical practice for understanding polar equations. Some of these things show up later physics classes or engineering classes, antennas or so-called Fourier series and so on. They have their applications, but a couple of years from now. Okay, until next time, good luck and God bless.